Want to quickly sketch an approximate bending moment diagram without getting bogged down in complex calculations? In this video, I will show you how to draw the most feasible bending moment diagram for any load case using simple calculations and bit of structural intuition. It's faster, it's easier, and still accurate enough for most practical purposes. This video is part of my series on IStructE certificate in structural behavior, but if you are looking to improve your understanding of structures, this video is for you. I will be solving 4 problems, guiding you through simple math and intuitive techniques so you can easily understand how the bending moment work for different load cases. So grab your pen and let's start sketching those diagrams. There are levels of drawing bending moment diagram if you want to understand basics of structural behavior. The first one is drawing bending moment diagram by using intuitive understanding of structures. Here, the values of loading and dimensions are not given, and all you have to do is to sketch the deflected shape. From there, find the direction of reactions, and from there understand the bending moment diagram or draw the bending moment diagram. And the example is this one, the one that you see on the screen. I have solved examples already in my earlier lecture. Have a look over here, click on this side of the screen. The second level is BMD, bending moment diagram with correct values, and that is using equilibrium equations. These are simple examples where you can apply simple mathematics, simple physics to find out bending moment diagram. Here, loading values will be given to you and the dimensions will be given as well, and all you have to do is to apply equilibrium equations. I have solved examples already in my earlier lecture. Have a look over here, click on this side of the screen. The third and most important level is drawing bending moment diagram approximately. Here the values of loading is given and the dimensions are given, but the structure itself is not a determinate structure, which means that unknowns are more than equilibrium equations. For example, in this structure you have 4 unknowns and 3 equilibrium equations. Now how do you solve this structure? You simply assume a pin, an internal pin somewhere along the length, somewhere where point of contraflexure is likely to pass, and in most of the cases point of contraflexure is located at 1/3 to 1/4 of the span from the support, and it will really depend on how much loading is applied. In this third level, I will be solving 4 examples to make you understand how do we apply these techniques to real structures. In this lecture, I want to focus mainly on drawing bending moment diagrams, but approximately. When we have indeterminate structures, which means that the unknowns or unknown reactions are more than equilibrium equations, then we have to make certain assumptions, and to quickly draw the diagrams, we need to assume internal pins as points of contraflexure, and in that way the indeterminate structure becomes a determinate structure, and then we can move forward. The learning outcomes of today's lecture will be to draw the bending moment diagram, approximately the most feasible one, and assumes point of contraflexure as internal pin. And using this method, we can solve indeterminate structures. For example, in these all cases, there will be change in the curvature of deflected shape at these points, and we normally assume these points as 1/3 to 1/4 of the span. When we have loading at the overhang portion, in that case, most of the time we assume that the internal pin is at 1/3 of the span. In this case, again, it will be 1/3 as well. But when we have loading applied to the entire span and at the overhang portion, in that case, the assumption is about 1/4 of the span. But remember that these are assumptions. If you carry out detailed analysis of these indeterminate beams, then certainly these points will be slightly away from 1/3 to 1/4 of the span. But at least it saves our time and we can solve a structure without needing a computer, and we can also compare our results with the ones obtained from computer as well. Here I will be solving 4 examples. Let's get started with first example. This is the first question. What is the most feasible approximate bending moment diagram for the load case shown? Here we have to find out the bending moment diagram as the loading is applied at the overhang portion, which means that deflected shape is going to be like this, and this means that the direction of reaction here is going to be downwards, here it's going to be upwards. So we have to keep these things in mind while solving these structures. Here firstly I will use process of elimination to eliminate certain options. I have 4 options here. This is not possible because we don't have any loading at all. This happens when we have a point load over here and we have support at this point. In that way we will have sagging over here. So this is completely impossible. The second one is option D, which is wrong as well. At a fixed support you will always expect some kind of bending moment, which is not here. That's the reason we will eliminate this option. And due to the direction of deflected shape, the slope should be 0 over here. It should not be something I drew it quickly earlier, but the direction itself should be downwards. When it is downwards, it means that it is going to create moment on the sagging side and it will not remain constant. So sagging moment is this one. This means that the correct option is option B, but we will not always have this luxury of having options, so we should know how to approximately analyze this structure using simple mathematics or using rules of thumb. Let's now go ahead and solve this structure and we will see if we're getting this answer or not. Firstly, I will say assume internal pin at about 1/3 to 1/4 of the span. As in this case we have overhang portion and loading is only applied at overhang portion. So here I'm assuming pin to be at 1/3 of the span. Span is 5, so 1/3 of 5 will give me 1.67 meters. And I will draw the drawing again. I have a pin over here and then a roller support and then a point load of 12 kilonewton. This is 3 meters, this is 2 meters, and the distance from here to here it is 1.67. These all dimensions are in meters. This is 3.33 meter. Now here I will isolate the right side and I will try to find out the reactions. So let us isolate the right side and I call these points as A, B and C. So isolating the right side will give me this diagram, 3 meters and 2 meters. This is 12 kilonewton and here it is 3.3, and I'm assuming that this pin is a pin support. So this is similar to this one. This is C, this is B. Summation of moment at C is equal to 0 because this is a pin. Starting from this 12 kilonewton load, so 12 times distance from 12 to point C is 6.33, and this is creating a clockwise moment with respect to C. That's the reason it is positive. And then I have this vertical reaction VB, which is creating anti-clockwise moment. So I will say minus VB times 3.3 is equal to 0. If you simplify this, you will get value of VB as 22.8 kilonewton. Once I've got value of VB, then I will find out VC as well. So there will be reaction over here because this point is simply isolated. VB plus VC is equal to total load, which is 12. And if I put value of VB, which is 22.8 plus VC is equal to 12, this will give me value of VC as minus 10.8 kilonewton. Now once you have got this value, then you can move to the right side. So on right side I have a pin. Minus 10.18 on right side means downward force at the pin, as pin will transfer shear force. So here I will have upward force of 10.8 on the left side and downward force on the right side. The distance here is 1.67. If the force here is upwards, then I should have a downward reaction over here, that is 10.8. And if this force is creating anti-clockwise moment, then I should have a clockwise moment over here. So 10.8 times 1.67, 10.8 times this 1.67, this will give me 18.1. So clockwise moment, kilonewton meter, from left side will generate a sagging moment. Now I'm ready to draw the bending moment diagram. So bending moment diagram will be like this. So we will have diagram like this. Over here I will have 12 times 3, this distance is 3, this is creating 36 kilonewton meter, and this moment we worked out little earlier is 18.1 kilonewton meter. So the closest option that we have is option B, which has 36 over here and 18 here. So the right answer is option B. Let me move to the second example. We have to find out most feasible approximate bending moment diagram for this load case. Remember that now we have loading applied on the entire span and overhang portion. In this case, we will assume that the pin or point of contraflexure is 1/4 of the span. Span in our case is 5. Again, assessing these options, option B is not possible because here we have a moment. This is not possible at all because it's a free end. At free end, moment cannot develop. Secondly, option C is not possible as well. I'm using process of elimination to come up with the answer. This is not possible as well because you have 0 moment over here. Option D and option A. Option A looks closer to me because both reactions are going to be upwards. When you have upward reactions, you will have hogging moments at these points, and because of UDL you will have some kind of sagging moment. So option A is the right option. Here in option D, this is wrong as well because moment is in sagging over here. Because of continuity, because of fixed support, it is going to go in the hogging region. So correct option is option A, but let us assess using our logics of points of contraflexure as pins to see which option is correct. Here firstly I will assume pin or point of contraflexure at 1/4 of span. Span here is 5 meters. 1/4 of 5 will give me 1.25 meters. So here I have a pin and this is 1.25 and this distance is 3.75 and distance here is 1. Now I will isolate the right part. So isolating this part will give me a pin support over here and distances are 3.75 and 1 meter, and this entire bit has got UDL of 4 kilonewton per meter. And I'm considering this pin as a pin support. I call this point as C, I call this point as B, and we have a reaction here VB, and call this reaction as VC. Treat this point, this internal pin, as a pin support. And from here we will see how we can find out the reaction. So summation of moments at C is equal to 0. We will have VB times 3.75. This is creating anti-clockwise moment with respect to C, so that's why it's negative. Plus I have 4 times the entire distance. Entire distance is 3.75 plus 1, which is 4.75, and the total load here will be acting at half of this distance. So 4.75 divided by 2, this is equal to 0. If you simplify it, you will get 12. So VB is equal to 12 kilonewton. When VB is equal to 12 kilonewton, the total load here is VB plus VC. This is equal to 4 times 4.75. 4.75 is this distance, so this is equal to 19. And if I subtract value of VB, VC will be equal to 19 minus 12. This will give me 7 kilonewton. So VC is 7 kilonewton. Once I've got this loading, then I can draw the left side diagram, and I can have this pin. This distance is 1.25 meters. VC is 7, that is clockwise from the right side. So if it is 7 kilonewton on the right side, from left side it will be downward 7 kilonewton, and we have UDL of 4 kilonewton per meter. So this loading will generate moment over here. So when loads are downwards, then the reaction here will be upwards. So VA will be upwards, and when loads are creating clockwise moment, then the reaction moment is going to be anti-clockwise. So MA, which is reaction moment, I will call it as a negative moment because it's a reaction one. So these loads, and that will be equal to loading from these loads. So 7 times 1.25 plus, in fact I will take it as negative 4 times 1.25 times 1.25 divided by 2. This will give me 11 minus 11.875, or I could say that minus 12 kilonewton meter. This is the reaction moment. So reaction moment is anti-clockwise, 12 kilonewton meter. So once I've got the loading, this overhang portion, this will create a moment of 4 times half of 1, 4 times 1 times half of 1, which will create 2 kilonewton meter, and here I will have 12 kilonewton meter anti-clockwise, which will generate hogging moment. So correct option is option A. But now if you want to find out value of this sagging moment, then you will need reactions first. So for reactions, the reaction over here VB is known to us, which is 12. Again, reaction at A is going to be equal to what we have applied over here. So 7 kilonewton plus 4 times 1.25, so that will give me 12 kilonewton. So reaction is 12 kilonewton. Now to find out where is the maximum sagging moment, which is the 6 kilonewton meter, I need to plot the shear force diagram, and where shear force is 0, that will give me the maximum bending moment point. So let me find out shear force diagram for this portion, starting from the pin. So at pin we have a reaction of 7 kilonewton upwards, so at pin, and then we have a roller support here, so we have 7 kilonewton here, and then we have this overhang portion. Between this point and here we have UDL, and it is spread over 3.75, so 4 times 3.75 is 26.25. So 7, take away this UDL 4 times 3.75, that is minus 15, plus 7, that will give me minus 8. Then at this support I will add up the reaction at support B, and VB was 12 plus 12, and it will give me 4. And again we have a UDL, so it will be like this. So this is SFD. This is the point where maximum sagging moment will happen, and this distance is 3.75 minus x, and this is 8. So comparing these two triangles, horizontal divided by vertical is equal to 3.75 minus x divided by vertical, which is 8. So this will give me 8x is equal to 26.25 minus 7x. So this will be 15x is equal to 26.25. X will be equal to 26.25 divided by 15, which is 1.75. So this point X, where there will be maximum sagging bending moment, it is 1.75 away from the pin. Now we are ready to find out the moment at this X. So moment at X, if I take it from left side, M at X will be VC times 1.75, and that is creating a clockwise moment minus 4 times 1.75 times 1.75 divided by 2. VC is equal to 7, I think. So from here we can find out mx. It's giving me 6.125. Approximately I can say that this is equal to 6 kilonewton meter. So option A is the right option. Let me move to the third example. Here again we have to find out most visible approximate bending moment diagram with this overhang portion, and the loading is applied at overhang portion. When loading is applied at overhang portion, normally we take this as 1/3 of span L. Span here is 4. Let us see the options. Option B is not possible. Use process of elimination because 0 fixed end moment is not possible. It's difficult to say which one is right from option A and option D. So this load is coming down as well, so I'm not sure which option is, and it's very difficult to say if it can be option C or not. So let's find out by calculations. So let me say assume a pin at 1/3 of the span. Span is 4. This is 1.33 meters. Let me draw the shape now. I have a roller over here. At the end I have a UDL of 6 kilonewton per meter, and this is 1 meter, and now this distance will be 1.33, and this is 2.67. everything is in meters, and then I will isolate it into right span, kilonewton per meter. This is 1 meter, and again from here to here I have 2.67. the reaction here will be VB, and if I call this point as C, the reaction will be VC. We're treating this point as a pin support. This is internal pin. In that way we will be able to solve the question. So let me say summation of moments at C is equal to 0. So let's find out moment due to this 6. So 6 times 1 times half of distance of will be 0.5 plus 2.67 is this distance. This is creating clockwise moment, so that's why it's positive, and then negative VB times 2.67. So if I simplify this, I will get value of VB as 7.12 kilonewton, and VC plus VB is equal to total load. Total load is 6 times 1. This is 6 times 1. So if I put value of VB over here, then I will get value of VC as equal to minus 1.12 kilonewton. And when you've got value of VC as well, then simply you draw now you can draw the diagram. Here it's negative on right side 1.12. If it is downwards, then it will be upwards actually on the left side 1.12, and this distance is 1.33. If the force is upwards, then the reaction here should be downwards 1.12. When the reaction is downwards, it is always going to create a clockwise moment or sagging moment. So moment will be clockwise here, and it will be equal to 1.12 times 1.33, so 1.48, or I can say 1.5. So moment here is 1.5 but in sagging. So now you can draw the bending moment diagram. This option C is the correct one because we have 1.5 over here and we have 3 kilonewton meter over here. 3 kilonewton is pretty obvious because 6 kilonewton per meter is applied. 6 times 1 times half will create 3 kilonewton per meter. So correct option is option D. Let me now move to the fourth and final question in the series. Here we have to find out most approximate bending moment diagram. A point moment of 10 kilonewton meter is applied here because the loading is applied only at overhang portion. So I will assume a pin or point of contraflexure at 1/3 of L. L here is 3. That will be 1 meter. Let us see what options do we have. We have 10 kilonewton meter, that is clockwise moment. Clockwise moment on right side, it will generate a hogging moment. So all of them have hogging moments. And option C is not possible because it looks that we have a point load over here, which is not the case. We go back here, we don't have any point load here. And option D is not possible as well because it feels that there is no change in moment. However, the reactions can be different. And now I'm a bit stuck between option A and B, and we will see which option is correct. Option B seems correct to me because this looks 1/3 of the span and this is looking like a half span, but we will see which option is correct. So first we will assume a point of contraflexure at 1/3, and this will give us 1 meter. So I will say assume internal pin at 1/3 of a span. 1/3 of 3 is equal to 1 meter, and then I will isolate this portion. The point moment of 10 kilonewton meter is applied. This is 1 meter, and from pin to here it will be 2 meters, and reaction is here. I call it as VB and call this one as VC. Internal pin is treated as a pin support. So summation of moment at C is equal to 0, and a clockwise moment is applied. So clockwise I will say is positive, and minus VB times 2, it is anti-clockwise, that is equal to 0. So from here VB is equal to 5 kilonewton. When this is 5 kilonewton, then I will say summation of moment at B is equal to 0. So when you say summation of moment at B is equal to 0, then you will have VC times 2 plus clockwise moment is positive 10 is equal to 0. From here VC will be equal to minus 5 kilonewton. So the direction of reaction is not upwards, it is actually downwards. So once we have this direction, then we can draw the right side. We have a pin over here, we have a downward reaction 5. It means that on left side we will have upward reaction of 5, and this distance is 1 meter, and 5 is creating a anti-clockwise moment with respect to fixed supports. So reaction moment will be clockwise moment. So 5 times 1 will be equal to 5, and if the load is upwards over here, the reaction load here will be downwards. So now I have 10 kilonewton meter moment over here, then I reach over here, then there's nothing happening. The reaction moment itself, it came out to be 5 over here. It is a clockwise moment, so clockwise moment from left side. If you have this member, if you draw a clockwise moment, it is going to sag this element downwards. So that's why it's going to be in sagging. So sagging moment is 5. The correct option is option B. All other options are wrong.